Hello everyone, it's Ray Gallucci, now retired. This is going to be my first talk at the 2019 Chappell conference. This talk will be about intrinsic redshift in quasi-stellar objects, QSOs. And then the question is it due to mass dependence and quantization? Just how does that fall out?
Just a little closer to the mic.
Okay. As an overview, I'm going to focus on the lifetime work of Halton Arp, Chip Arp, about quantization of intrinsic QSO redshifts. The relationship between redshift and QSO mass will be examined, and the fact that both the redshift and the mass may be quantized, which was the subject of much of his work. My approach will be mathematical only. I'm going to see some geometric explanation for the fact that the redshift seems to be proportional to mass to the 2/3 power. I'm going to look at the quantization theories proposed by Arp, Su, and Tift, and I'll examine the mathematical plausibility of the first two. The third one is too complicated for me to figure out, but I will present it. The concept of new galaxies forming from old galaxies was first suggested by M. Bartsunian in 1958. He had a theory that new galaxies are ejected from old ones, such that the high redshift QSOs may be linked to low redshift galaxies. This was a non-cosmological explanation for redshift, as opposed to the current mainstream that the universe is expanding and others basically saying redshift correlates with distance from the Earth. The theories that were first suggested were then continued by Tift publications in '63 and 2013, Arp, major publications, '87, 2003, Narlikar in '89, Burbage 2001, 3 by Bell 2002 through 7, and Lopez, Corredora, and Gutierrez in 2006. So this idea is about 60 years old, and it has been explored over the years. There's been an observed periodicity in the redshift, denoted by the letter Z. This periodicity has been observed at the values of 0.3, 0.6, 0.96, 1.41, and 1.96. There's also predictions that it should occur at 2.63 and 3.46 by Bajan and Flynn in 2007. And there have been some observations at a very low redshift of 0.061 by Ratcliffe in 2009, and Arp himself addresses this lower redshift. Many explanations have been offered. There's Dopplerian explanations, tired light, varying gravitational constant, interaction between radiation and cold Rydberg material, three-dimensional quantized time, oscillating atomic lines, oscillating galactic luminosities, and the three I'll talk about, one called quantum temporal cosmology by Tift, a theory based on ether and gravity by Su, and what Arp developed as variable particle mass. Here's the QSO data for redshifts from 0.2 to 2.0. This is taken from Su's work, the reference at the bottom. You can see that for the various ranges of redshift, there's the observed numbers of quasi-stellar objects. They're all well into the thousands. There's a logarithmic relationship of the mass of the ratio of the quasi-stellar object to the sun's mass, and as you see there, as the redshift increases, the projected mass relative to the sun's mass also increases, going out as high in the 9th increment to about 2 billion masses of the sun. This is the formula for a gravitational redshift, which has been proposed as one of the explanations for the quantization and mass dependence. There's a fancy formula up there, which is a limit formula. You can see familiar terms, the graph constant, mass. There's essentially a radial coordinate, which is analogous to the classical distance from the center of gravity. Then there's the distance to the observer, our friend the speed of light. And if you solve the above in the limit and equate it to a measured value of z for the redshift, you come up with the radial coordinate, or the classical distance to the center of the gravitational mass, shown as the formula below. If we take the QSO data that I showed previously from Su, using the sun's mass of approximately 2 × 10 to the 30th kilograms, that is equivalent to an effective radius on the order of about 1 to 6.5 trillion meters. The QSOs objected from parent galaxies, however, should be much smaller than this in order to correlate to the redshifts that we've seen. Recognize the Milky Way radius is 2.5 times 10 to the 19th meters. It's 6 to 7 orders of magnitude larger than the measured value of R star for the sun. So if typical of galaxies from which the ejected quasi-stellar objects have been observed, the quasi-stellar object must be quite small relative to the parent nucleus to generate the observed redshifts solely by gravitational effects. So it seems a little bit of a stretch to postulate that the observed redshifts are due solely to gravity. How about tired light as an explanation? As light travels outward from inside the quasi-stellar object, it loses energy through interaction with the matter inside the object, which is presumably a plasma, according to a typical formula for attenuation with distance, which is an exponential type decay. We have the energy at a distance r from the source, the emitted energy E sub 0, and an attenuation coefficient, usually shown as mu, which is inverse meters. Therefore, the redshift at a distance from the source, which is measured as the difference in the frequency to the emitted frequency, and using the energy for a photon, E equals h nu, we come up with this formula for the redshift, which is basically an exponential type decay. Let's assume that the emitting nucleus of the quasi-stellar object has a relatively constant size. Let's assume it's spherical. It does not change in size, but loses mass as the material emanates outward. Therefore, it undergoes a decrease in density. Attenuation is a function of this density, as shown by the correlation with the attenuation coefficient. It decreases with decreasing density, so as you go through less dense object, there's less attenuation. Therefore, the redshift that would occur would be less as the QSO ages and it attenuates. Since density and mass are directly proportional for a constant value, we can rewrite the equation for a linear regression as the natural log of the redshift plus 1, and it's just a constant term plus another term times the ratio of the mass of the object to the mass of the sun, m0. When I took the data shown before for SU for the redshifts, the best solution that satisfied this form had an R-squared correlation coefficient of about 89%, which is fairly good for these types of analyses. However, it did give me a different trend. The observed redshifts now show slightly decreasing rate of increase with mass, and that was contrary to what I got to the best fit for tired light attenuation, which I'll show on the next slide. Here's a series of correlations that I obtained. The one here at the top, this is the one that used the linear correlation, which had the R-squared of 89.1%. And as you trace it here, you see that rather than be concave in this direction, it actually goes in this direction, where it goes underneath some of the observed ones. So while its R-squared is fairly good, it doesn't have a really good fit to the observed data. I did 4 other correlations. You can see one here, and then the 3 here that are highlighted in yellow. The fits that were highlighted in yellow show the 3 best, although none will actually pass through all the observed values. Of the 3, the equation with its dependence on the scaled mass to essentially the 2/3 power, that's this one here, you can see the scaled mass is to essentially a 2/3 exponent, shown in red, suggests a possible physical phenomenon for the dependence of the QSO redshift on mass, given the previous assumptions. So as suggested by the regression analysis, light presumably is emitted at the surface of the quasi-stellar object, taken as an approximate sphere, such that its surface area will be proportional to the square of the radius. With the assumed radius of the emitting nucleus portion of the QSO being constant, again that was an assumption, any decrease in mass results from a decrease in density, as mass emanates outward with the growing QSO, but not the growing emitting nucleus. Since the radius is proportional to the cube root of the mass, given the relatively constant volume that we've assumed, we then find that the surface area will actually be proportional to mass to the 2/3, which lines up with the correlation that we found. If this relationship is true, then the correlation with mass to the 2/3 power follows. For a relatively constant emitting volume and surface area, decrease in density means a decrease in the redshift. A possible mechanism again returns to the attenuation effect, although this is somehow directly proportional to the radius, that is, the distance through which the light must pass to reach the emitting surface. With this decrease in density and relatively constant radius, the attenuation decreases, allowing light to pass through more readily. There's less energy lost, therefore a less decrease in frequency, which corresponds to less redshift. The light retains more of its original, in quotes, color. Now let's look at the concept of redshift quantization, which is primarily based on the work of Halton Arp. I found this presentation that he gave in 2000 in Portland on YouTube, and it's a very interesting presentation, runs for about an hour, and I've taken some quotes directly from his presentation here. What he said was in the early 50s, they saw thin connections between galaxies and radio lobes going from the central galaxy out to the lobes on either side. This material is actually being ejected. That's the only way you can get this configuration, although mainstream will say that it's just pure coincidence that they line up. If the galaxy is going to eject something, it's going to eject along the path of least resistance, which means it would go out the poles. You have this nice relationship that as the quasars proceed out as time goes past, they age and drop and prefer quantized redshifts. That is, when they're first ejected, they have their highest redshift and they're closest to the emitting galaxy, and then they proceed outward with time and their redshifts decrease. What Harp interprets this to mean is that these quasars move out, evolving to low redshift. And he has a lot of interesting pictures for various galaxies showing how the redshifts shift as the quasi-stellar objects move out from the galaxy along with distance. Again, all that's on his presentation on YouTube. So here I took the three correlations, the three best regression fits. You can see at the top, one was proportional to the square root of the scaled mass. One's proportional to the logarithmic of the scaled mass. This is the square root, the logarithmic scaled mass. This proportional to the mass, the scaled mass to the 2/3 powers. And what I did is for the values of the five Z quantization peaks, I calculated what the scaled mass should be, and then I took an average of the models to show what values I'd like to work with here. For the three best regression fits, I estimated the QSO mass at each of the main 5 redshift peaks. If there's a quantization phenomena as the QSO is ejected and travels outward, redshift decreasing in specific increments, we expect that there has to be some relationship between redshift and therefore mass of the QSO with time and or distance. And the time or distance increment 1 being associated with the newly ejected QSO. So this is actually time increment 1, which has the highest Z peak and shows the highest scaled mass. And increment 5 associated with the oldest redshift. That's the one on top at 0.3, and the scaled mass is the lowest by about a factor of 10. So time actually goes up here, showing that we start out with the highest redshift, quantized down to the lowest, the highest quasi-stellar mass, down to the lowest with time. Two of the equations that I looked at, those 3 equations I looked at earlier, 2 of them have the undesirable property at time or distance increment 5. You can see here that a couple of them drop off below 0 at increment 5. The exponential curve here, and that's the purple graph, which is probably a bit hard to see, but it fits the best. It passes through all the quantized values. Almost as good as the natural log curve, this one here. They both have tremendously good correlation coefficients. Again, there's only 5 data points, 99%, 100%. The inverse time correlation here, showing time to the -1, a little bit higher than 1, but basically inverse time, that's the one in green, is a slightly weaker correlation, but it's still pretty high and it's still acceptable within the limits of accuracy. So the question I ask is, do any of these, the yellow highlighted correlations, suggest a quantization mechanism? I don't answer that question, I just ask that, and then I return to Arp's explanation here, which is variable mass. Again, from this presentation he gave in 2000. The solution Einstein made in 1922 involved an approximation which Arp thinks was wrong. The approximation was that particle masses were constant everywhere in the universe. With this approximation, you end up with the Big Bang solution, which predicts expanding space-time coordinates. You compress back to the Big Bang singularity at time zero, and all the redshifts have to be velocities of the recession, which the mainstream says is just the universe expanding outward from the Big Bang. Narlikar and Hoyle made the assumption that the particle masses didn't have to be constant in time. When they did that, they ended up with a very simple solution that the masses varied with the square of time. As time went on, they communicated with more and more of the universe. The masses did that, and increased in mass, and it's also a theory known as Machian theory. If the electron mass, when it makes its transition in the atom and emits the photon, is small, the photon is weak and it's redshifted. As the electron grows in mass, again Arp is postulating variable mass increasing with time, as the electron grows in mass, the photon that is emitted is stronger and it has a greater redshift, or a decreased redshift. So this is a perfect explanation for what we've been seeing, that younger objects are high redshifted, and it means that the sacred Hubble constant just turns out to be the inverse age of our galaxy. It's got nothing to do with recessional speed, etc. Arp continues to say that if you start with the galaxy nucleus, you have a high density. In the center of this active nucleus, the mysterious engine where matter is created, new particles are in that environment. They gain mass from the environment very rapidly. Once they come out of the nucleus, ejected as a QSO, they go into a different, much lower density environment in the bulge of the galaxy. And then if they come out in the plane of the galaxy or along the axis, they drop here into the local group surrounding the galaxy. These involve enormous drops in density, which will be shown on the next slide. Finally, as they move out further, as these objects move out further from the local group of galaxies, there's another step down. Again, he's postulating it's not a continuous drop, but a stepwise decrease in the redshift and the increasing mass. These particles will be gaining the mass very rapidly. The redshift drops very rapidly, lessens very rapidly, and then it levels off, and then it goes into another step in the drop. He estimated there are just about 6 drops at 6 major quantization levels, the 5 that have been historically postulated, and the 6th one, the smallest one at 0.06. And this is a composite of the diagram that he gave at that talk. It shows the incremental increases in particle mass. We have particle mass in this along the x-axis, and quantized drops in redshift along the y-axis, starting with the galactic nucleus. So that's step 0. It's the smallest mass and it's the highest redshift. There's then a drop as it goes out into the galactic bulge, which is a drop in mass, which is an increase in mass as we go out the x-axis, a drop in redshift. Next, from here we connect over to this part. I couldn't fit it all in one. So we get to step 2. This is the galactic plane for axial ejection. Next we go out to the local galactic group, which is number 3. Finally, when we transfer over to this graph here, we go into the galactic supercluster, which shows the greatest mass and the lowest redshift. And then he didn't go any further, but he postulates there may be further step increases in mass and drops in redshift. So this is basically the variable mass theory from Halton Arp. Now C.C. Su had another explanation for the quantization of redshifts. He thinks it might be a gravity-induced type of quantization. This is from his work in 2006. His ejection model, he says that quasars form from the gas of atoms, plasma, and dust that are ejected from the parent galaxy. Together they form a local ether. The gravitational potential on the surface of a quasar is extraordinarily strong. That leads to a wide variation in redshift, which can be ascribed to a variation in density and size of the gas cloud. So different gas clouds can be released which have different densities, different gravitational strengths. And so the quantized redshifts actually form when the quasi-stellar objects are ejected. It's not a step decrease in time as Arp postulates, but it's just that 5 or 6 different quantized values of mass and redshift form from initial conditions. It can be due to the strength of the initial ejection from the parent galaxy, the speed at which the cloud moves away from the parent galaxy, how the gas expands, how the gas cloud fragments, and finally how the stars are formed. Due to a non-uniformity in particle velocity and density, or to some internal disturbance, a quasar may break off into pieces of identical or similar sizes. He postulates that fragments are spherical, the density remains unchanged, therefore their radius is shorter than the previous one as they come out for each step by 2 to the minus 1/3, and the gravitational potential on the surface of either fragment decreases by the square of that 2 to the minus 2/3. So after splitting in half n times, the gravitational-induced intrinsic redshift is given by this formula here. And we'll look at this term specifically in the next slide. That term denotes 2 times the normal gravitational potential corresponding to the 0th redshift, Z0. For the very high redshifts, he was able to come up with this correlation formula. 1 plus Z sub n is approximately equal to this value here. And taking the 1.96 value as the 0th redshift, which is the highest one that's usually observed, this formula leads to the prediction that the preferred intrinsic redshifts, he actually gets a range of 14 of them. He actually goes back to an n to the minus 4, which has a very high redshift of 6, and stretches it all the way down to the last observed value, which is the 0.06. And he manages to align with 5 of the 6 observed redshifts here. And if you average these two, the 0.71 and the 0.49, you get the 6th observed redshift at 0.6. So his formula and assumptions are able to reproduce the redshift peaks, and he says that they are expected to be smeared since other affected factors of uneven splitting, gas expansion, and star formation will accumulate with time. Unlike Arp's theory, Sues does not postulate that the series of quantized redshifts represent a QSO evolution with time and or distance, although he does agree that the QSOs are formed by ejection from a parent galaxy. His quantizations are static for each QSO and are dependent upon variations in the initial conditions and interactions until the QSO stabilizes and exhibits one of the characteristic preferred redshift values. So Arp has a evolutionary type theory where basically a QSO is always ejected as a high redshift. Its mass increases incrementally in steps with time. And as the QSO jumps to a higher mass, it exhibits a lower quantized redshift. Sue basically says if there are 6 different QSOs exhibiting the 6 different quantizations around a galaxy, all 6 of those were ejected with different initial conditions, and their redshifts are stable at the values that you see. It just so happens that they form into these quantized groups. Now, Tiff's developed a theory called quantum temporal cosmology, which is fairly difficult for me to follow, and so I didn't do any analysis with it, but I'll present it because it is interesting. He theorizes that time is a 3-dimensional phenomenon. He calls it tau space, with matter, which he calls sigma spaces, flowing out radially from a near singular origin in time. I'm not sure this has any correlation to a Big Bang or anything, but this is how he describes it. With the decay of energy, doubling processes produce quantization, define properties of matter, and generate observational effects. There are 2 expansions from the point of view of galaxies, which are effectively particles in this tau space that he postulates. There's a temporal, which is a radial, and a spatial, which is a lateral expansion as the timelines grow, and separate sigma spaces. Sigma spaces are space, which seems to resolve the dark energy problem. The dual redshift prediction in quantum temporal cosmology appears to fit supernova data. I'll show that on the next slide. The different structure further indicates that if you look back geometry in three-dimensional time, you end up with a logarithmic spiral. The present maximum observed redshifts are far from the origin on this spiral, since the dual expansion in quantum temporal cosmology is absent in classical cosmology and is ascribed to dark energy. So he does retain some of the assumptions of the mainstream, though maybe not their explanations, where he uses the term dark energy, but not in the sense that a mainstream physicist would use it. And this basically is an illustration of his quantum temporal cosmology. We see here he talked about a logarithmic spiral. As we go out, you see that the redshifts decrease, starting here as high values 11.2 down to 0.24. The different structure further indicates that looking back geometry in three-dimensional time corresponds to the logarithmic spiral. The figure at the right, that's this figure here, illustrates this time-time look-back geometry, time versus two time axes, with observed redshifts as marked. That's the values shown here along the logarithmic spiral. Present maximum observed redshifts are far from the origin. Now, if we look at, this is his illustration of what he calls the tau space, time being three-dimensional with matter in sigma spaces. So he has these three dimensions here. And then the dual redshift prediction in quantum temporal cosmology appears to fit the supernova data. And his QTC, which is the middle curve here, seems to fit well with the observed data points shown. So like I say, I really can't explain his QTC, but it is another explanation for quantization of redshift. So having tried to absorb all this, I did my own speculation here. Starting with Arp's work, the QSO quantized redshift varies with distance from the parent galaxy. This could be either or both a time or distance phenomenon. The QSOs are ejected with high redshift, which seems to correlate well with high mass or density, provided the emitting nucleus remains relatively constant in size. Arp based this observed quantization. He believes there's a variable particle mass increases with time and distance as the particles evolve and travel outward from higher to lower density regions in piecewise, not continuous manner. So if you accept Arp's variable mass postulate, this explanation appears reasonable. That was my conclusion here. Again, I'm usually just examining plausibility for these concepts. If I look at Su's theories, he holds that the quantized redshift and mass results from the initial conditions and subsequent interactions. It's not an evolution like Arp's. The spatial distribution around the parent galaxy, whereby higher redshifted QSOs are closest and the lower ones are farthest away, is a result of the initial energy of the QSO's ejection, its initial size, and how it interacts with surrounding material. The more energetic ones travel outward farther, interact more with material, thereby losing more mass, and they show the lower redshift with distance. So he explains the fact that the QSOs that are farthest from the parent galaxy have the lowest redshifts as a result of interaction and energy and various energetic phenomenon, as opposed to Arp saying that the ones that are farthest out have been traveling the longest and undergoing the most mass increases. So although Su was also able to predict at least some of the quantized values, he does not offer a definitive reason for the quantization aspect of it. There's no reason to expect his theory to, why it would be continuous. So I found his theory to be somewhat less plausible than Arp's. And I can't really comment on TIFFs because it's beyond my expertise. I tried to look at this mathematically and see if there might be a physical basis that might fall out of all this. My simplest equations that reproduce fairly well the quantized decreasing QSO redshifts as a function of uniformly increasing time or distance intervals were suggested as an exponential decay or roughly decay as a function of inverse time or distance. Exponential decay is a fairly common physical phenomenon, such as radioactive decay, but the discrete aspect, the fact that it drops piecewise, appears to be unique to quasi-stellar objects and their redshift. An inverse distance dependence is characteristic of a magnetic or electric field around the infinitely long string of charges or current carrying water or wire. And this is the type of theory that you'll find in electric universe, which has intergalactic Birkeland currents pervading the universe. Galaxies form when these currents flow could exhibit surrounding magnetic or electric fields with the inverse square dependence, decreasing with distance. What is more difficult to ascertain is, again, why is it quantized? I make the following mathematical observation that the quantization of both QSO mass and redshift can be represented by a sine curve with decreasing amplitude of the same decaying exponential form as my previous equation. And here's the analysis I did. It's an absolute value equation here. I have a value 2.73 e to the plus 9, which is the scaling factor corresponding to the quantized masses. This value here in the sine function is a shift factor that enables me to reproduce the 5 of the quantized peaks. And the masses that occur at these, measured by the redshifts, these are these 5 values here for increments of 1 through 5. Again, the highest one is first, the mass decreases with time. And these actually compare fairly well with what were the observed values to within 10%. And I'll just give an example here. If you look back here, these were the observed values from the peaks based on the regression values. They range from 1.65 to the plus 8 to 2.05 to the plus 9. And again, 1.65 to the plus 8 compares with 1.78, 2.05 to the plus 9 compares exactly with this. So again, I was able to get comparison with observed values within 10%. I don't know what phenomena might exhibit sinusoidal behavior with exponentially decreasing amplitude, possibly some form of harmonic dependence. I only offer this as food for thought. So in summary, my approach to the topic of quantization of intrinsic QSO redshifts, especially based on the lifetime work of Halton Arp, was purely mathematical. Developing a theory for intrinsic quantized QSO redshift is beyond my expertise. I did postulate a geometric explanation of intrinsic redshift that's possibly dependent on mass to the 2/3 power, related possibly to the attenuation of light energy and therefore frequency within the emitting nucleus of a QSO, compounded by a further dilution and therefore energy and frequency increase due to spread over the surface area. So it's emitted, and then it's emitted based on the density of the emitting nucleus, and then over the surface area it decreases more with the 1/r² function of a sphere. To do the quantization aspect justice, I summarized 3 theories by other experts and examined the plausibility of the 2 that are within my realm of capability. And then lastly, I offered a mathematical representation of the quantization aspect as food for thought, not that I can explain it. And all this leads to is a time for change with the mainstream thoughts of Big Bang, etc. Thank you.
Questions?
Yeah, it's Bob. Was heat anywhere considered in any of their theories and yours? Heat of the emitting star?
I didn't come across that. It may have been implicit in some of Sue's speculations.
Well, you know, it seems that a heat with vibrating atoms give a lot more energy and thrust in some cases, and when it's cooler, it doesn't. It would seem to have some impact, but it seems very complex in terms of age and distance and time.
It might have been a bit implicit with Sue. He talks about, due to the strength of the initial ejection from the parent galaxy, that implies maybe some sort of heat type of energy expulsion. But it's it's implicit at best, not explicit from what I saw. Unless there's something buried in Tiff's theories that I can't uncover.
Of course, the problem is it's how do you quantize the heat? That doesn't run too well.
Yeah, why it's quantized is, I mean, unless it's somehow related to quantum mechanics and energy levels and things like that. But again, that's a microscopic scale versus this macroscopic scale. So I'm not really, even ARP explains why the masses increase and the redshifts decrease, but he doesn't really have an explanation for why it's a quantized phenomenon, not a continuous.
Now, I always thought that Halton Arp, so he was famous for showing that the redshift is not actually due to distance, right? That was
correct. It has nothing to do with the distance of the QSO from Earth. It does have a distance relationship from the emitting galaxy.
So you're showing, I just thought it was interesting that there is a quantization. I've never heard of this quantization. So you're saying that within these objects, and these objects are like connected to their galaxy or something like that?
Yeah, we don't have something to draw on, but if you look at his website, he has pictures of different galaxies. And you'll have something like a Milky Way galaxy, the plate here with the bulge, and then there'll be a series of quasi-stellar objects, usually along the polar axes above and below it. And associated with each one of these will be a redshift, and the redshift will be lower for the objects that are farther away from the original galaxy. Now, of course, mainstream will say, well, that quasar that has the very high redshift just happens to appear as if it's near that emitting galaxy. It's actually billions of light years further away because its higher redshift means it's shooting away faster. And Arp and others found that there's, I guess, the probability of that being true for all these observed galaxies is some ridiculously low number that you just can't, it's almost impossible to deny that these QSO objects have a relationship to the galaxies that they are seen closest to.
So they're going beyond the galaxy, beyond the objects.
They're ejected from the galaxies. They eventually may become galaxies because they grow in mass. As they move outward, their redshift decreases and they get bigger.
But they're not physically connected to what they think is the parent galaxy.
Well, in a way they are. There's one picture he shows with the emitting galaxy, and then there's like a gas spiral out to the first quasar. So he's, at least the ones that are closest seem to have like a gas stream coming from the emitting galaxy. Then I guess as they go out farther, the gas stream dissipates or whatever. But the closest ones, at least in some of his pictures, are clearly connected to the emitting galaxies. It just can't be coincidence that all of these that he's observed are coincidences. But mainstream will say that it just so happens that they align that way. So
what would you say is a summary of your main contribution that you're doing here?
My main contribution here, which is basically to see again, I don't come up with theories, I look at other people's theories. It's that Arp's explanation, if you accept that there is quantization, then it's plausible and supported by mathematical models of increasing mass and decreasing redshift with distance away from the parent nucleus. And it's a little less likely that Sue's explanation that it's more of a gravity phenomenon and that these various QSOs are created from the parent galaxy at stable but quantized redshifts and masses. That one is, I think, a little less likely. I think Arp's explanation is probably more likely, but I can't explain the quantization aspect.
Any more questions?
I have a
No?
question. I don't understand some of the terms like when you use the term nucleus, I think of a galactic nucleus
Yeah.
of an ejected stellar object.
Yeah, yeah, it's basically, if you look at pictures of quasars, they're relative to the galaxy from which they're ejected, you're very small, very bright, very high redshift. So one of the theories is that what the galactic bulge, the parent galaxy, a piece of that for some reason gets ejected. And so basically what you have is a tiny bulge that's been ejected, very dense. So it's a galactic daughter nucleus, much smaller than the original parent nucleus. And that's what a QSO initially appears as, and then it gets more tenuous with time. As again, this is Arp's theory. It gets more tenuous with time as it moves out and increases in mass. And as it gets more tenuous and increases in mass, it's less redshifted. But he finds that this occurs in piecewise steps, because whenever he looked at when he was a mainstream physicist astronomer, he observed, he spent thousands of hours at telescopes photographing galaxies, and he and others repeatedly saw that next to these galaxies, all these quasars would line up at these specific redshift values near the parent galaxy. So he didn't see a continuous group of redshifts, he saw these quantized values. They do decrease with distance, but it's stepwise. And so, again, his variable mass theory doesn't require a quantization. It just basically says as time goes on, mass increases, redshift decreases. So that part of it explains the fact that the QSOs that are farthest from the emitting nucleus have the lowest redshifts. But the mechanism that makes them quantized, he never was able to explain. And I don't think there's been an explanation for that yet that I've seen.
Well, the quantization is new to me, but I remember when Arp was explaining how a galaxy near in spatial orientation to another galaxy had a different redshift, so I remember that from Arp.
Yeah.
I didn't know the difference between QSO and quasar. Are they?
They're essentially the same thing. Quasi-Stellar object and a quasar are pretty much considered the same. He uses the term, I think he goes more with the QSO term to keep it separate, because if you use the term quasar, then your kind of mind sets into the concept in mainstream physics that this is a new galaxy being born independent from anything else, racing away from us and in mainstream cosmology, a quasar is a young galaxy, from young in terms relative to the Big Bang, because it's racing away the farthest, so you're looking back farther in time. It's basically a galaxy as it was 10 billion years ago. That's the mainstream explanation for quasars. Arp's is that, no, it's about the same age, it's coming out of an existing galaxy. Its material is about the same age as the existing galaxy, but it has a much higher redshift, not because it's racing away at any high speed or anything. It's an intrinsic redshift due to the fact that mass increases with time.
The data that you use for your regression analysis, did it include, apparently there's some 50 to 60,000 data points in this represented in table 1?
Yeah.
Is that true?
That's the number of QSOs that fall into this range, and apparently they found that they fall pretty well into these quantized intervals. Yeah, this is the number of QSOs that have been observed in the various ranges. This is taken from Sue's work.
So that periodicity is really hard to explain then.
Yeah. I don't know what it is, and I haven't seen anybody really explain it. Tift may, again, I don't really understand Tift's theory well enough. He did seem to allude to an explanation. The dual redshift prediction. Well, again, he just says, as energy decays, doubling processes produce quantization. But again, he doesn't say, the only thing one might be applied when he talks about doubling processes, he talks the fact that there are two expansions from the point of view of galaxies. So he's talking about, his cosmology says that there's tau space and sigma space, and there's a temporal and a spatial expansion. So he's got a factor of 2 in there, buried in there, and this leads to a doubling process and possibly the quantization. So he, I think, believes he has an explanation for the quantization, but again, it's his theory's beyond me.
It sounds like a space warping theory to me.
I don't know. Time being three-dimensional, doesn't compute with me either, so.
I'm not aware of how redshifts are calculated or represented. So Z, which is the...
Oh, that was the formula. There was the redshift formula.
These are from spectra that are shifted from
this is the redshift formula. It's
absorption
different.
spectra of known.
Yeah, like that, if there's a sodium emission line or something like, or sodium absorption line, and it's normally at, 10 angstroms, and then when you observe a quasar, you see that it's at 5 angstroms. That's a shift in frequency of a certain amount relative to what it should be, so then you just plug it into the form. The 10 angstrom frequency goes here, the 5 angstrom frequency goes here, you divide by the 10 angstrom frequency, and you get a Z of, I guess in this case you get a Z of 0.5 or something, and then that's...
So that's basically a unitless dimension.
Yeah, it's a ratio of wavelengths or a ratio of frequencies. And it does assume a constant speed of light.
Thank you. Thank you.
So we have a question from our live Facebook from Jim Martin. He says, Ray, has there been any further research on ARP's QSO concepts?
I didn't come across any. I mean, I looked for, his work, he died, about 10 years ago, or more than that? I mean, when I was looking at you see most of the work, all the work I came across here is pretty much a decade old. I haven't found anything more. Oh, no, TIFT, 2013. Okay, so I haven't found any work by any of these other guys other than TIFT, so I would say the only work that I'm aware of that's been done since ARP. Now again, I wrote this paper a year or 2 ago, so I haven't checked back to see if anything's happened recently, but when I checked 2 years ago, the most recent material I found was TIFTs.
Adverting to Halton Arp's adverting to Halton Arp's work, does it have application to black holes? In this sense, conceiving a black hole to be an area where, particularly a supermassive black hole, where galaxies and stars and everything conceivable is gobbled up and drawn in by massive gravity, and then expelled via the axes of the black holes, thus spewing into space the material that is necessary to create new galaxies. To your recollection, did he go that far in
I
his...
didn't see any discussion of black holes or anything like that. He didn't. I mean, the only thing getting ejected along the axial lines were the ejection was always from a readily observable galaxy. He never said that he saw anything. Now, he probably could, if there are black holes and they're in the center of galaxies, they may be unobservable to see anything coming out along the line. So I didn't come across anything like that with his work. I'm not an expert on Halton Arp. Again, I think there's a book he was Seeing Red. I think he wrote a book, and I watched a couple of his videos and read some of his websites, but I'm not an expert on all his theories.
Thank you. I think the book Seeing Red may answer that question for me. Thank you.
I have an observation.
Sure.
I just wanted to say something about.
I think it's incredible, and I thank you for getting the data. There's like 50,000 data points here.
I didn't collect them.
And so you
Sue made that list, I just took his list and.
But you used regression data, or did you use data from the table?
I just used the table. I just reproduced his table. This was, he had a table that, this is basically a table that came out of this report by Sue.
So you used
I just reproduced
summarized
this table.
data of these many data points?
Yeah, he did this, somebody did these calculations here of the log of the mass, etc., and I just converted over to the sun's mass.
My comment is for researchers that want to examine these things to have access to the data such as what you did here, and I think it's a very good idea to capitalize on. So thank you.
Also note that this was 2006, so I don't know how many more QSOs they've picked up since then.
Any more questions? No?
Thank you.